So we'll start with finding the domain.
A little blurry.
Yeah, I just want to write a few things before I focus. Otherwise, the autofocus won't work on the camera. See, find the domain. Let me write the functions down. Let's do something like 3 minus 2 log of, let's say 7 minus x. There it goes. And then let's do one more. Let's do a harder one. G of x is equal to, let's say log base 3 of 5 minus 2x over 3 plus x. So the first one's fairly straightforward. It's just a log function, but with some shifts and stretches applied and some flips, our standard transformations. But the only rule that's going to break, or the only rule that determines the domain is that the inside of a log must be positive. There's no square roots, no rational expressions or anything like that. So we use our rule, the third rule we came up with, that the inside of a log must be positive. So we take whatever's inside the logarithm and set it greater than 0. And in this case, we just add the x over. And so we get x is less than 7. In our domain, minus infinity up to 7. What kind of brackets do we want to use there? Square brackets or round brackets?
Round.
Round brackets, right? Strictly less than, no equals to. So we use the round brackets. And that's all there is to it for that guy. This one's going to be a little bit more complicated. Again, only a log function, but we do also have this rational function inside of it. So we do know that at least by the denominator can't be equal to 0, we'll have to have that x cannot be negative 3. There's maybe one rule we can apply. Now, the other thing we have to consider is that the entire expression inside of a log is strictly greater than 0. So that is our domain defining inequality. And now we have to remember how to do these. So we want to create our number line. And what do we need to plot? We need to plot the zeros of the denominator and the zeros of the numerator. Zeros of the denominator, hopefully everyone can see, is negative 3. And because it's a 0 in the denominator, so you get in the habit of maybe putting an open circle around that negative 3. And I put this vertical line as an indicator that that would be an asymptote. Since we cannot divide by 0, anytime there's a 0 in the denominator, those create our vertical asymptotes. So I just maybe put a few dots to remind myself that the vertical asymptote, we can never include it. In a domain or in calculus, you'll get into intervals of increasing, decreasing with rational functions. And wherever the zeros of the denominator, never included. We also want to plot the zeros of the numerator. So check that real quick. It's going to be a fraction. So we should get 5 halves when we set that equal to 0. And then what I would recommend doing is putting the appropriate circle here as well. But since our inequality is strictly greater than, again, we're going to have an open circle. In calculus, in future problems where you're doing inequalities, polynomials, rational functions, if you have an equals to, you want to put closed dots because you can include those if we had a greater than or equals to, and that might occur with like a square root function as well. but denominators again.
I had a question.
Yeah.
Shouldn't it be negative 5 over 2 because there's a minus sign?
Yeah, so solve that. You get 5 minus 2x. When you add the 2x over, it becomes positive.
Oh, okay. Got it. My bad.
Yep. So I've got the circles included, so we know that I'm never going to include that point, not going to include this point either because it's a strictly greater than. And now what do we need to do? We got to determine whether this function, whether the rational part of this function is positive or negative in those three regions. So we pick test points. So let's pick an easy one. Let's say 0. At 0, we will get 5 over 3, which is a positive number divided by a positive number. Overall going to give me a positive. Pick a number over here. Let's say x equals 3. 5 minus 2 times 3, 5 minus 6 will give me a negative number in the numerator. And the denominator will be 3 plus 3, positive. So our domain in this case, or excuse me, our overall expression in this case is negative. And then we pick another test point in the left region, x equals negative 4. We plug that in. Now it's 5 minus 2 times negative 4 is negative 8. So minus negative 4 is plus 8. Excuse me, minus negative 8 is plus 8. So it'll be a positive in the numerator. But with a negative 4, we will have a 3 minus 4. So negative in the denominator. Overall, we've got a positive divided by a negative. Gives us a negative. And once you're done with these number lines, go back to your inequality. Look at what we're asking for. Since we want greater than 0, we take the positive values. So our domain in this case is going to be minus 3 to 5 halves. And neither end is included. Okay, so go ahead if you want, pull up IC 14 if you want to follow along, or I'll just write out the problems here. I want to keep doing this on paper, so I don't want to share the screen or anything like that. Most groups, I think, got through number 1, which is a very important one, making sure you get all the rules straight. So let's go ahead and take a look at number 2 and number 3. Let's do number 2B. I'll leave A to you guys. We've got log base 5 of 10 plus log base 5 of 40 minus 4 log base 5 of 2. So maybe we'll do this in 2 ways. The way we were doing it on Wednesday, the way I typically like to do these is to write the expression as a single log, because you'll have other problems involving that same problem statement. This one, of course, it says find the exact value of the expression, and we should get an integer. So let's go ahead and combine the logs. We'll have a log 5, and since I have addition outside the log, it turns into multiplication inside the log. And I'm not actually going to multiply it. I'm just going to write it as the multiplication, not actually perform the operation, not actually perform that multiplication. It'll just waste our time. We're going to write this guy as subtracting. The 4, we got to combine all of our logs. I need only logs, all the same base. And since this one has a 4 out front, we're going to use our property where multiplication outside of a log turns into exponentiation inside of the log. So that'll be log 5 of 2 to the 4th. And now we're subtracting logs outside, which is going to be division of the arguments inside. So we'll have a 10 times a 40 over 2 to the 4th. And now what you want to do is factor the numbers that aren't factored entirely. This 2 to the 4th is in its prime factorization. 2 is a prime number, and we've got 4 of them multiplied together. But 10 and 40, we can break down a little bit more. So 10, 2 times 5. 40 is 10 times 4. So we can do it in steps. 4 times 10 over 2 to the 4th. We'll still have 2 times 5. Those are prime. 4 I can break down into 2 times 2. 10 I can break down into 2 times 5. And now still all over 2 to the 4th. So this one we had to break down quite a bit, mainly because we are looking to cancel out the denominators, which are 2's. But I've got 4 2's on the denominator and 1, 2, 3, 4 2's in the numerator. So all of those will divide. And we are left with those 2 factors of 5. So it'll be log 5 of, and let's actually just write it as 5 squared. 5 times 5. And that will simplify to 2. Now we have the base of the log and the exponential the same, so they essentially cancel out and we are left with the argument. Of course, the other thing you could do is now we could bring down this 2 out front as multiplication, and it would just be 2 times log 5 of 5, which is 1. So 2 times 1. Questions on that guy? So the other way we do it, we don't have a whole lot of time. Let's just maybe get it started real quick. You can break these things down in terms of the logs, essentially factoring while they're already split. So let's actually write 40 as like 4 times 10 minus 4 log 2. And so what you can do is this log 5 of 10 is actually, we can write as log 2, log 5, base 5 of 2, plus log base 5 of 5. Since 10 was 2 times 5, I can now use the multiplication property to addition property, and likewise do the same for all of these. So log base 5 of 4 plus log base 5 of 10 minus 4 log base 5 of 2. And now you can kind of see we keep going. I would want to write this guy as log base 5 of 2 plus log base 5 of 2. And now we would have log base 5 of 2, log base 5 of 2, plus another log base 5 of 2 is 3 log base 5 of 2 minus 4 log base 5 of 2. We can simplify those. And then, of course, we can get another log base 5 of 2 out of that guy. So you can do it this method as well if it makes sense to you. If you find it quicker. For me, I just find it almost more tedious. Even just writing it out, writing all those logs can be a little bit more tedious. So try it that way if you want to finish it on your own. Otherwise, let's take a look at number 3. Because number 3 has a lot of these expressions, powers of 10. It's a little weird because it's a matching problem, and it says match columns on the left with letters on the right. And there's no like discernible way of which direction to go. So the best way to do these is to look for the complicated expressions and simplify them. So some of the expressions on the left column look a little hard. Some of the expressions on the right are a little complicated, and we can simplify those. So let's take a look at B. And B has 100 to the log of 5 halves. So the things we want to look for in simplifying these expressions are anytime I have logs and exponentials playing together in some way, if I have a log and an exponent, or if we have an exponential operation inside of a log, there's going to be a simplification. we designed our log specifically for that, to undo the operations of exponential and vice versa. The problem is, in order to undo it properly, the bases need to be the same. We have to have the same base of the log and the base of the exponent. So here we've got a base 100, whereas the log is base 10. So that's going to be one factor that we need to mess around with these problems. The other thing that you want to look at is the operations have to be touching each other in some sense. They have to be in that sequence. There can't be any other operations going on. In other words, right now I have an exponential raised to a log. That's good. If there are constants, other constants in the exponent, we're going to have to work with those as well. And vice versa. If I'm taking a log of a number and there's other numbers times an exponential, we got to make sure to use our log properties to manipulate that first. We really need only an exponential and only a log directly interacting with each other without anything in between. So let's see. The first thing we want to do in this problem, so since there's no constants that we can play around with, we want to change the base. And nicely enough, 100 is 10 squared, which is the base of the logarithm. So that's the base we want. And then when I write 100 as 10 squared, we have an exponent to an exponent, which means those multiply. So inside the exponent, we have 2 times log base 10 of 5 halves. And we run into this other problem now. We want the 10 and log to cancel, to simplify, but they got to be touching each other without any steps in between. And we have this 2 here, which is problematic. So what we can do is if we just work inside the exponent, this 2 times log of 5 halves, we can use the properties of log. Multiplication outside of a log is exponentiation inside the log. So our goal was to get this, get the 10 and log touching each other. Then they cancel. Same base. So they undo each other, and we are left with just whatever's in the argument. So 5 halves squared, or 25 fourths. I think this should be letter M, so they round everything. 6.25 on the worksheet. Let's do one more. Let's do L. L has 10 to the log of 2 divided by 2. So similar things we're looking for. We want the bases to be the same and no other multiplication or no other operations that are getting in the way of the log and the exponential directly working at next to each other. And in this case, we almost have it, but we're dividing by 2. Bases are the same, but we have this division by 2 in the exponent. So really what we want to do is take a look at writing it like 1/2 times log of 2. So division in an exponent, remember, is always multiplying by a fraction. And we want to write it as a multiplication because multiplying outside of a log, we can write as exponentiation. So again, upstairs in the exponent, we can adjust that to be 2 to the 1/2 inside of the log. Now the 10 and the log, same base, directly working next to each other. Those will cancel, and we are just left with 2 to the 1/2 or square root of 2. Any questions on that?